working with Raphael A P and the whole team at the University of Warsaw, and I'm going to present our work with deriving the initial mass function of the bulge from binary microlensing events. So, a bit of the motivation of this work. So, the fact that microlensing depends primarily on the lens mass, not the brightness, and we have larger occurrence rates in crowded regions, makes it the only or the best method to probe low mass stars in the bulge, and consequently the initial mass function. So we have some works in the literature that uses large samples of microlensing events to get the IMF using Galactic models and so on. And they have they derive consistent slopes for the IMF, but they usually either neglect the binary events or apply a correction at the end. So, Calamida et al. In 2015 gets a luminosity function from HST data for the bulge. And to get the IMF, they assume several values of binary fraction and mass ratio distributions. So, for masses larger than 0.5 solar masses, they are more or less consistent, but lower than this mass, you have different IMFs. So, and there's no good constraint in the literature about these values. So what we want to get here is to get an automated approach, both for the detection and the analysis of binary events. So both binary source and binary events. And these large statistics and applying the detection efficiency, we get the binary fraction and mass ratio distribution and the best IMF for this region. So we know that the magnification of point source for today is given by the Kinsey curve. We have the three parameters there in terms of the master radius. And for binary source, it's quite simple. You have 5 parameters. The total magnification is the superposition of the PSPL, more or less. And the source separation is given in terms of the parameters. And the distance of the source. So just one example here, showing that depending on the way that the trajectories are aligned, you can get a clear bumps, or if you get farther from the sources, it can get confused by PSPL events, as Natasha showed yesterday. So, for example, this curve F can be misclassified. And for binary lens, the magnification is more difficult. It involves complex polynomials and usually generates caustic patterns, but solvable, and the length separation is given in terms of the derived parameter S. And here we have a clear parameter for the mass ratio already. So I use Hubble for proprietary data, observed between 2010 and 2020. I use all the alerts that we have in the websites. And at this point, we made a compilation of 800 binaries, looking at the literature and inspection of alerts. They are shown in red here. And from those, we selected a sample of a few dozen to serve as a benchmark in this study, which at this point is limited to light curves with well-separated bumps. So for this benchmark, every change that we do to the code, both for the detection and the fitting, this benchmark event should be detected. So I use the paper of Shemek Neruz, 2017, 2019, assumes a 360-day window to get the baseline flux and the sigma, and the bump is defined as at least 3 consecutive points above the 3 sigma, the baseline. And it applies some thresholds, assuming the PSPL fitting, and the number of bumps equals to 1. So usually the binary events are skipped in this algorithm because of some of these values and some other. Here is just an example of selected event. And some optimizations that I do to detect these binary events is applying 2 windows instead of 1, because, for example, if you get an event like this, so the window is here, and then it's this other bump is accounted as the baseline, so it would be skipped. Some other optimizations. So to flag the binary events, I check for a secondary bump. So let's say that I remove the points from this bump and check again if there is another bump. And it cannot have more than 2 because it would be another kind of variability. And we also apply a correction in the slope of the baseline. So this work from Galactic applies a complex method for this, but we saw that a single correction in the slope is enough. So we have some challenges like binaries similar to PSPL that may be skipped. We have several morphologies and false positives with the zero optimizations. So using the 9 high-frequency fields from 2017, we looked at 550 million light curves, and we retrieved almost all the PSPL events that are given in Hubble alerts. But regarding the binary candidates, we got 116 in these high-cadence fields, and that are within with these more strict thresholds that apply compared to previous work. So this corresponds to more or less 4% of the PSPL sample from Rus, 2017, and it's more or less consistent because they state that the binaries may account for 10% of the PSPLs, the correction. And here I'm using just one of the morphologies. And for the low cadence fields, we are still working on integrating the light curves to get the best combination of thresholds so we don't miss too many events. About the model fitting, I do it with some steps using the Newlands model code. So first, I get a quick binary source fit to get the minimum points between the bumps. So here the bumps are not well separated, but I just illustrate here that it's working for these kind of mixed bumps. So I split the data into 2. I fix the PSPL independently, and this gives starting parameters for both binary source and binary lengths, which I fix with MC and ultranest to get the evidence. So in this example, the idea is here. The binary length fitting was more favored. So we can see here the chi-square difference of 150 more or less. The cumulative distribution shows where this chi-square differs more, close to the bumps. Here the coordinate plots showing the correlations between parameters. And in this one, the binary source was more favored. The difference chi-square was of the order of 4, smaller. And in this case, we also look at the evidence derived for both fittings, the amount of negative landing flux, and the T prior that we apply. And the summary, that's the automated detection of these binary events throughout the Hubble light curves, worked very well. We got a low count of false positives for these events with well-separated bumps. I think in the future it may be useful for large data sets as Rubin and Roman. And the next steps, so the first two for our first paper with well-separated bumps, so apply criteria assuming the derived fits, apply detection efficiency corrections, simulating all the possibilities if it's detected, and for the future papers, analyze other morphologies, and finally get the constraints for binary fraction and mass distribution for the IMF. That's all. Thank you. Good.
So, what about the degeneracy in your binary fitting? How do you take those into account?
Yeah, so at this point we don't have too many degeneracies because we do not include the cases with calcium crossing and the more complex cases. Also, the parallax is not included at this point. So with these well-separated bumps, we don't have too many degeneracies to account yet, but we include them in the future works.
Did you use the VBAN data?
Sorry?
Did you use the overall VBAN data in your?
Yes, yes.
And does that, change any of the?
Oh, no, actually the IBAN is the standard ones, so standard light curves from the database.
Well, I mean, binary sources can have different colors in these sources. So
Yes, yes.
actually, it's good as well.
Yeah. Take it into account. Thank you.
I have one quick question. Do you plan to maybe improve the array or the associate?
Yes, at some point, yes. Maybe the next papers, which could be like depending on the derived parameters, you can apply some as well.